Good morning. Today we are going to discuss about the introduction to MOS inverter logic. So before going to MOS inverter logic, so today we are going to discuss about the basics required for MOS transistor logic. Practically, every modern system contains digital integrated circuits as critical subcomponents. So it is essential for a system design engineer to understand about digital ICs. The capability to integrate a number of transistors in a single IC are increasing day to day. So an application specific IC is required for high volume applications. The general design style of any digital IC is represented by using NMOS logic gate, even though it is currently losing its power. The construction details of NMOS transistor are shown in below figures. So as per the diagram here, I think you can see that there are two blocks which have been saved. One is the symbols of NMOS transistors here, then simple NMOS logic gates. The logic gates are used to take one or more inputs and produce a single Boolean output by applying a Boolean function. Most of the digital ICs are based on binary logic, where the signals represent a 0 or a 1. In binary logic, the input is considered to be a 0 if its voltage is below the gate threshold voltage, whereas the input is considered to be 1 if its voltage is above the gate threshold voltage. The simplest logic gate is an inverter which has an output that is the complement of its input signal. The symbol of inverter is shown in figure 1.1. So the first one which represents the symbol of the inverter, where A is the input and B is the output, which is equal to the inversion of A, and the B, which is the Boolean function of the inverter with input A and output B. So when A is 0, then output of the B is inversion of A, which is 1. So the 1.1b elevates the simple realization of inverter using a resistor and N-channel MOS transistor. Here the resistor is acting as a load here, and we are using the Q1 transistor, which is an N-channel MOS transistor, and applied input voltage is referenced as VA, and output is taken at a drain, which is of VB. So the inverter shown in figure 1.1 is similar to a common source amplifier. If the gate voltage is small, let's take the example where in the figure 1.2a, the entire when the input is 0, so we are deriving the output voltage here. When input is equal to 0 in figure A, so then the current path between drain to source is open. So there is no path between the drain to source, and the current goes to be 0. So the output voltage is VDS, which is high voltage. So the output is now moving to high level. The gate voltage is large or greater than V threshold. Let example is figure 1.2b. Here the input voltage which is greater than the V threshold voltage, it is equal to 3.3. Then so as it is more than threshold voltage, there is a path established between the drain and source. The entire current goes to the ground, and the output at the drain is equal to 0. So the N-channel MOS transistor is considered to be the voltage control switch. Consider that the transistor is not ideal, so the transistor is replaced by a small resistance when the transistor is on, and is shown in figure 1.3. So this is the circuit diagram. So previously we considered that the transistor is in ideal conditions, and we have not considered any resistance within this transistor. Now in practical conditions, it is when it is not ideal, it is replaced with a small resistance called RDS, which is the resistance between the drain and source terminals. So, based on that, the output expression has been derived. It is equal to VDD, that is supplied voltage, into the RDS, because the voltage drop across we are taking across RDS, divided by the total resistance present between the VDD and the ground, that is RL plus RDS. When the switch is closed, then the output voltage is not zero. So when the switch is closed, the output is not equal to zero, but it is given by Vout is equal to VDD into RDS by RDS plus RL, which is slightly larger than zero voltage. As long as RL is much higher than RDS, then output voltage is not zero, but much less than the gate threshold voltage. In figure 1.1b here, that resistor RL will take up too much area, because when you go for construction design of the resistor takes more amount of area, so need to be replaced with n-channel MOS transistors. So normally the inverter in figure 1.1b would never be used in an actual ICs. So in NMOS technology, the resistor RL is replaced with an n-channel depletion transistor and is shown in figure 1.4. So it is a typical inverter in an NMOS technology where the resistance is replaced by this transistor. The depletion transistor Q2 operates like a resistor but occupies less chip area. To obtain a low output voltage when the input is a 1, the width to length ratio of the drive transistor Q1 must be less than the width to length ratio of the load resistor. So a more complicated gate can be realized by adding more drive transistors. Drive transistors are the transistors that have their gates connected to an input signal. Q1 is the drive transistor in figure 1.4. NOR gate realization using NMOS technology. NOR gate has a low output if any of the inputs are high. The realization of NOR gate using NMOS technology is shown in figure 1.5. So this is the realization of NOR gate using NMOS technology. The first one, which represents the symbol of NMOS, the symbol of NOR gate, where this represents this is a Boolean function of the NOR gate. For the transistor realization in figure 1.5b, if any one of the inputs at a high voltage, if any one of the voltages at high, then the output, any one of the input is high, then the output goes to 0. The corresponding transistor can be approximated by a closed switch and the output voltage is pulled low. If the inputs are at low, then all the drive transistors will be off and pulls the output voltage high to VDD. So, thank you.